Okay, so on Wednesday we wrote this function as a series, and what allowed us to write that function as a series? What was the general idea that allowed us to write that function as a series? Okay, but what's the principle that allows us to write that? Yeah. Yeah, and what is that? A over 1 minus r. What is that? Sum of a geometric series, right? So if we have a function that kind of looks like a over 1 minus r, then we can rewrite it as a geometric series. And that's what we started working on. So we got that, and here's a form of that answer. I think our form looks a little different than that. What do we have? Negative 2 to the I, and then x to the 2i plus 1. So that's just another form of that same thing. For some reason, when I put in the final answer we got in GC, it for whatever reason doesn't work, but this works, and this is equivalent to what we got. Okay, so notice that I'm graphing here y equals, I'm graphing partial sums, right? Capital N would be like, if I increase n, I'm getting a longer and longer partial sum, right? So right now, so if I do n equals 0, that's the first partial sum. And when I do that, I get this line right here. So the first partial sum of that series we found gives us this line, and you see that at 0, it's doing a good job of approximating the function that we started with, right? And then, as we know, as you take more and more terms, you take a longer partial sum with more terms, you're getting a better and better approximation of the series, right? With each term that we add, we get a better approximation. So here's the second partial sum with n equals 1. And then et cetera. Every time, so n equals 2 would be actually the third partial sum, because the first partial sum is for j equals 0 or I equals 0, which you guys have. And so what happens with each term that we add, so you see how this thing is reproducing that function. Better and better. But what? Why isn't it approximating the function out here at 1.8 or 2? So here's, I can go all the way to n equals, here's n, I'll do 19. N equals 19. So that's like to the 20th partial sum. I've got 20 things, the first 20 terms added together. And the purple one is the graph of the partial sum. And the gray graph was the original function that we were trying to approximate. So why doesn't it approximate, say, the function at x equals 1.2? Scott knows. Yeah. It's alternating because it's an alternating series. Is that what you mean? No, that's not the reason. Yeah, I wonder. Okay. Okay, so there's an interval of convergence, right? So it's only true for certain x values that this series will approximate that original function. It's not true for all x values. So is it from -1 to 1? So I'm showing a pretty, here's 20. So is it from -1 to 1? No, it's something else, right? It's like something less. It's a smaller interval than -1 to 1. So we want to know what that is. How do we find out what that is? How do we find out the interval of convergence? Alec? Maybe?
Where you like set what you have, like what you had, and then like set it in there and solve for x. Is it that?
No, that was when we actually got an interval and we were checking the endpoints. So how do we actually get the interval? Yeah, Noah. Right. So the ratio test, given a power series, the ratio test is going to tell us for what values of x it converges. Or in other words, what values of x the series is going to approximate that function. All right, so so you got lots of practice of the ratio test, and we need the time for something else, so we're not going to do it. But it turns out to be square. When you do the ratio test for this one, square root of 2 over 2 plus or minus square root of 2 over 2. So now I've turn those off. So here's the original function from square root of 2 over 2 to 2. Okay, and then here is the so the one that's still flipping up and flipping down is for the series from negative square root of 2 over 2 to square root of 2 over 2. And so if we took a larger partial sum, then eventually we'd get a better and better approximation all the way to here.
It's like root 2 over 2 is the same as the square root of a half.
Mm-hmm. Yep. Yep. Yeah, so now that blue part of the function is all that the series will ever be able to do. And you see, like, even at the ends there, it's still not doing a good job. So we need a lot bigger partial sum to get it accurate at the very ends of the interval. Okay. Any questions on that? So yeah, so you should do the ratio test on that, and verify that in the end you get this interval of convergence from negative square root of 2 over 2 to square root of 2 over 2, or the square. That's the same as the square root of 1/2. Square root of 1/2. Okay, so let's do another example. So we did this one. So that's the one we just did. So what about this? Now we're going to actually have to find 1 over 1 plus 2x. Looked at those two quickly. Okay, but that's super easy, right? Because this is just like a over 1 minus r, so we can just write it down. Thank you for pointing that out. That could have dug a bad hole for us. Okay, so 1 over 1 plus 2x. Can you write down what that is as a power series? Should be able to. Write down what that is as a power series. Everybody. Right? Because this is like what? A over 1 minus r. So, okay, everyone write it down. What are you going to write right here? Okay, Caitlin, did you get it? Very good. So first we got to think of this as 1 minus negative 2x. And then our a is 1, and our r is negative 2x. And we know that for a power series, starting at I equals 0 would be a r to the I. Okay, now we're going to write out several terms here. Another important thing that you should be able to do. So given that series, I want you to write out maybe the first 3 or 4 terms. Let's do the first 4. Write out the first 4 terms of that series. So when you see that, you think what, right? You see that, you think what? Okay, Jordan, did you get a couple terms there? What's the first one? Negative 2. So negative 2x to the 0. So anything to the 0 is 1, right? So when I equals 1, what will you get when I equals 1? Negative 2x. When I equals 2, 4x squared. And then I equals 3. Okay, you guys got it, good. All right, and then and so on, right? And so on. Okay. So what are we doing? We saw x over 2x plus 1 squared. We said, with this square here, it doesn't match the form a over 1 minus r. So what are we doing instead? Instead, we're working on the next closest thing that we could write, which would be the easiest thing we could write, be 1 over 1 plus 2x. Because we know if we took the derivative of that, we'd have something like f. Do you see? We can't do it because the whole bottom is squared. But what we can do is 1 over 1 plus 2x, whose derivative is really close to f. That's the scheme that we're following. Okay? So then we're ready to do it. Now on these problems, I really, really encourage you to use this organizational format that I have. Okay? I think it just really helps to do. We got actually 3 different forms of the same thing. We got the function, we've got the sigma notation, and then we have it written out. And when we take the derivative now, we're going to take the derivative of all 3 and make sure it all adds up to be the same thing. All right, so we're going to do h prime. This is the derivative step. And when we do h prime, we're going to get, so derivative of 1 over 1 plus 2x is, it's like 1 plus 2x to the negative 1, right? So we want the derivative of that. It's going to turn out to be negative 1 over 1 plus 2x. Yeah, I was doing 1 plus 2x squared. Done? Chain rule times 2. So you get negative 2 over 1 plus 2x quantity squared. Okay, so, but all forms of this we're going to take the derivative of, okay? So we're going to take the derivative of that, we're going to take the derivative of this. So what's the derivative of this? So now we're just going to apply the power rule to the general term there. So when we do the power rule, we do what? Bring the I down in front, times negative 2x to the I minus 1, times negative 2. Okay, and then we're going to do the derivative of the polynomial. This is the easy part. Derivative of 1, 0, minus 2, plus 8x, etc. So here's the nice thing about this. We're pretty confident about our derivative of each term of the polynomial, and it's a nice way to check to see if we did this part right, which is maybe a little, we might not be as sure about because we haven't done this before, taking the derivative of a general term like that. Okay, so when you plug in I equals 0, so when you start plugging in these terms, do you get that series? You can check. When I equals 0, we get 0. When I equals 1, we get 1 times negative 2x to the 0 times negative 2. Is that right? Negative 2. When I equals 2, 2 times negative 2 is negative 4. Times another negative 2 is 8x to the first. 8x. See what I'm doing? I'm using the individual terms to help me check to make sure I wrote this right. Now, is h prime the same as f? No. So, but it's an easy adjustment, right? What do we need to do to h prime to get f? we've got we got to get rid of the negative, we got to get rid of the 2, but then we also need an x. So what are we going to do? Multiply by negative 1/2 x. Everyone see that? And then I'm going to do that to every single thing. I'm going to do it to the function form, to the sigma notation, and to the polynomial form. So this is multiplication. So times. Is that better? If I take h prime and multiply by negative 1/2 x, I will get f. And that's what we wanted. Right? So when I do it here, I'm going to get f. When I do it here, negative 1/2 x times this is x over 1 plus 2x quantity squared. That's what we wanted. So that's what we're going to do to this as well. So the negative 1/2, notice the negative 1/2, we'll just make that go away, right? Negative 1/2 times negative 2 will be gone. And then we'll also have one more x. So how will that change this? We'll have I times. We got to be careful here, all right? Because we want still want I minus 1 negative 2's, but we want one more x. So we got to split this up. So we need negative 2 to the I minus 1. We don't want to change the number of negative 2's multiplied, but we do want to change the number of x's. So how many x's will we have now? I. One more x makes x to the I. Okay. If I lost you, please ask. Yeah. Because we need f has the denominator squared. This is not of the form a over 1 minus r. But by taking the derivative of this, what we started with, h, we get 1 plus 2x squared. So there it is. I took the derivative. Yeah, it's just like, it's kind of being clever, right? It's like using a trick, using calculus and a trick. We can do 1 over 1 plus 2x easily. Take the derivative. Now we have something very close to f. Yeah. Yes, please.
Can you explain how you got the sigma notation for f of x?
For f of x. So you see that everything's going to get multiplied by negative 1/2 x. Do you see that? So the negative 1/2 and the negative 2 went away, first of all. So the negative 1/2 that I'm multiplying. So now I'm going to multiply what's left here by x. So, but we can't just change this exponent because that'll change the number of negative 2's. Right? So I'm going to split that up. I still want to have I minus 1 number of negative 2's multiplied together. But I don't want I minus 1 x's because if I'm multiplying by x, I want one more x. So that bumps my x up to I instead of I minus 1.
So you're splitting the negative 2.
I need to split this apart so that I can only increase the exponent on x, not the negative 2. Yeah, so it's negative 2 to the I minus 1 times x to the I minus 1 is what that thing above means. So when I multiply this thing by x, that won't change, but this gets bumped up by 1. Okay, sure. Thanks for asking. Okay, and then same thing with this. We're going to multiply all these by negative x over 2. So we'll get 0 plus x minus 4x squared plus 12x cubed. All right, and again, I really recommend that you do this so that now you've got something you're pretty confident in to check this, which you may not be as confident in. And this is what we need, right? We want the power series. So plugging in I equals 0, 1, 2, 3, do you get these terms? Let's try it. When you plug in 0, do you get 0? When you plug in 1, you get 1 times negative 2 to the 0 times x. Checks out, right? Plug in I equals 2. 2 times negative 2 to the 1 times x squared. Does it check out? Yeah. Okay, so it's checking out. So I think we got it. There's the power series for f. Okay, and again, you remember in web work, they'll say this is a power series like this. And they just want the CJs. So sometimes they'll ask you to write out a partial sum, or they'll ask you for this general term, but often they'll also say, what's C0? What's C1? What's C2? Okay, and what is, say, C3? C3 is the coefficient when the power of x is 3. So this one will be 12. C2 is the coefficient when the power of x is 2. Negative 4. If it ends up alternating powers, right? You get all the odd powers, but no even powers, then all your even coefficients will be 0, right? Is that a question worth asking the whole class? No? Okay. All right, questions on this example. So are we done? We have to find an interval of convergence, right? So then you would do the ratio test, and you'd find out for exactly what values of x does this legitimately approximate f, right? It's not going to be, it might be for all x, but probably not. It looks like it's going to be, looks like it's going to be, I don't know. We'd have to do it. But we know there's going to be there's often some radius of convergence, some interval for which the power series actually reproduces f, and then outside of the interval it will just diverge, right? It won't reproduce f. Okay, questions on this example? So ratio test for interval of convergence. All right, let's do another one. This one. What do we know how to do again? No. What do we know how to write power series for? A over 1 minus r. What do we have? Natural log of 1 minus something. So we don't know anything about power series whose sum are something with natural log, but we do know something like 1 over a over 1 minus r. So what could we start with, and what could we do to get something like natural log of 1 minus r? Yeah, Micah.
We want to take the antiderivative for this one?
So antiderivatives. Antiderivative of a over 1 minus r, natural log? It's like, what's that? Antiderivative of 1 over something, right? Is natural log, right? Because natural log, the derivative of natural log is 1 over. So antiderivative of 1 over something is the natural log of that thing. So we want to start with what? We want our, let's call, say, I don't know, p of x. So what function can we easily do that's going to help us get this one? 1 over 1 minus x squared, right? Because we know the antiderivative of that is something like natural log of 1 minus x squared. But then we got to think about this. We got to take the antiderivative of this. And so remember, we worked on our techniques. It would sure be nice to have what when we're doing the antiderivative here? What we're going to do is this, is the antiderivative of this ln of 1 minus x squared? No. No. There's a problem, right? So what would it sure be nice to have? Thinking about our techniques. What's that? An x in the top, right? Because we could do then, that would be undoing the chain rule. Do you see that?
Yeah.
derivative of 2x squared would be the x. So we've got, in the end, we want x squared times natural log of 1 minus x squared. So we're going to start with x over 1 minus x squared, because we know we have to do the antiderivative of this, and that sets us up to make it easy. Okay, so here we go. We need the so we got a times r to the I, and for simplicity's sake, we don't want to do the power rule on that, or yeah. So for simplicity's sake, this is the same as x to the 2i plus 1. Good. So rewriting that as x to the 2i plus 1. See that? Think what? Should be easy. We got what? So when I is 0, we get x, right? When I is 1, we get x cubed. I is 2. One more. Good so far? And then what did we want? We want antiderivative. So I'll just put a little integral sign to represent antiderivative, and then we're going to do that to everything, right? So antiderivative of p natural log 1 minus x squared. And what else do we need here? Almost. Also. Oh, the x is taken care of by the chain rule. We need something else. Negative. Right, negative. We need the function whose derivative is x over 1 minus x squared. That's undoing the chain rule, right? When we take the derivative of natural log of 1 minus x squared, we're going to get a negative 2x. We got the x, but we have a negative 2 that we don't want, so we're going to multiply by negative a half. Okay, so now we're going to do the antiderivative of x to the 2i plus 1. Antiderivative is going to be, new power will be x to the plus 2, and then we'll have 1 over 2i plus 2, right? Antiderivative power rule, right? Antiderivative power rule. Again. And then this is the easy part. Antiderivative. 1 half x squared plus 1/4 x to the 4th. 1/6 x to the 6th. And 1/8 x to the 8th. Okay, lots of things going on. So if I lost you, if I ever lose you, please ask. There's lots of things involved in these problems. Lots of things at once. Okay, so does starting at 0 get us this here? So if I start at I equals 0, do I get these terms? So when I equals 0, 1/2 x squared, right? When I is 1, 1/4, it seems to work, right? So this is really helpful to check to make sure we did this right? So when we actually think about the sum of those series, the terms, is it the same as the antiderivative of this polynomial? And it is. Okay, so now this thing that we have now, how are we going to get j out of it? So what are we going to do to what we have to get j now? So times what? We got to get rid of the negative half, Negative 2x squared. When we multiply this thing that we have now times negative 2x squared, we'll get j. Because the negative a half will go away, and we'll inject the x squared that we need. Yes, please. Oh, let's see. So that, yeah, we should probably do that. I think that when we do the ratio test at the end to get the interval, I think that will work itself out. You're right. When you do an antiderivative and you're using ln antiderivative, you should have absolute values there. So we'll just put them in. Yep, you're right. I'd have to think more about that in terms of the implications of having or not having them in this setting. I'd have to think more about that. All right, so then we get j. So times negative 2x squared. So we can we'll put the negative 2 on top of this fraction. There's the negative 2. And then x squared will do what to this? X to the? 2i plus now 4. 2 more x's on every term, right? So we're going to add 2 to the exponent because we're multiplying by x squared. And then our terms will be negative x to the 4th. So times negative 2. We'll make these all negative. Half as much and add 2 to the exponent, right? So minus 1/2 x to the 6th minus 1/3 x to the 8th minus 1/4 x to the etc. Dot dot dot. And then we ought to check those, right? So by putting in I equals 0, I equals 1, I equals 2 into this, we ought to get those terms. Okay, this can be simplified, right? We got a 2. I can factor out a 2 of the denominator, factor out 2, and reduce. So we can rewrite this as. And we should, easy simplifications, we should definitely do like that. Negative 1 over I plus 1, x to the 2i plus 4. Do the ratio test, get the interval of convergence. What's the other thing I was going to say? I just blanked. There's something else I needed to say about this. Oh, right. What would C0 be? So here's our first 4 terms, starting this, going this way, right? C0 would be? C1 would be? There's no x to the first term. C2. There's no x squared term. C3. Okay, do you understand? Now C4 would be negative 1. This one starts at negative x to the 4th, so all your coefficients from 0 up to 3 will all be 0 because there's none of those terms. Okay, so these are harder problems because they involve so much reasoning and so many things going on. So start tonight and email me. So use the email instructor button on the web on the web work if you have questions, or get into office hours. But don't wait till tomorrow night to try these. These are harder, as you know.
Yeah.
homework, so we will have to see.
I had a question. Are you going to get more quizzes during the semester? I haven't been there, like, I haven't had one in a while.
Maybe. Why? Are you gonna not come if I don't have quizzes?
No, the opposite. I want more quizzes.
What's that?
Just raise my grade. Just more quizzes is better.
More quizzes is better?
Oh, for me.
Okay, cool. All right. Good to know. Here. Is this what we got? So what we got right there?
Yeah, because we can fact out the
Okay, good. That's good. I did it right.
I like these. I did watch your lecture over the weekend. Did all the homework over the weekend.
Okay.
And they're fun. Like we were really dead on Sunday at work, so I just got to sit down and do all day
Nice.
long, and I just like loved it.
Yeah, they're neat problems.
Yeah, I like stuff.
And it's cool to graph. Like, I wish we had more time to graph them and see how they converge on the actual function and stuff. So,
After the test, we should be able to send out a file like this so we could see kind of how to construct it a little bit more.
you could send it out now.
I'd be curious sometimes. I like checking my answers a lot and just like make sure I'm doing it right.
Oh yeah, for sure. Yeah, there should.
Self-checking.
Yeah. Yeah, I'll find one and I'll send it out.
Thank you.
Yeah, sure.
I get to be a hermit longer.